Welcome. In this lecture, we shall be doing a few problems on the root finding methods for single equations. So, whatever I have taught you in the previous lecture, we shall be implementing those methods here. So, first let us go to this particular problem. In this problem, we find this kind of problem many a times in the fluid mechanics, and similar kind of problems you will also find in other engineering applications, even in the chemical kinetics. So, here in this particular problem, we find that we have a turbulent flow of a fluid in a hydraulically smooth pipe, where the Prandtl number universal resistance law relates to the friction factor and Reynolds number according to the following relationship. Now, before we proceed to the solution, let me just give briefly some idea about what this particular problem means. Is this that whenever a fluid is flowing through some pipeline or over a surface, due to its own viscosity and also the flow rate with which it is moving on the surface or in a particular closed pipeline, it will have some kind of resistance to its flow, and this flow resistance may be found out by knowing the viscosity, and sometimes when the flow is laminar, we can find it very easily by in terms of Reynolds number, which signifies the type of the flow. And type of flow means that it could be laminar flow, it could be turbulent flow, or it could be somewhere in between these two types of flows. More about this, the nature of the flow you learn in fluid mechanics or fluid dynamics courses. So, this problem pertains to the evaluation of a factor that is we call the friction factor, to know how much resistance a fluid would encounter when it is flowing over a surface or in a conduit. Now, how does this knowledge help us? This knowledge is required by us whenever we are trying to design a system, and in this system either we are pushing the particular fluid by using a compressor or using some pump, and depending on the friction factor, the resistance to the fluid flow will change, and then we can understand that how much will be the power required for a pump and compressor. So, for all these reasons, we often need to evaluate the friction factor. And second use of the knowledge of friction factor is that sometimes we need to find out the rate of heat transfer or rate of mass transfer in terms of heat transfer coefficient or mass transfer coefficient. Many times we find that for many systems these two coefficients are not available directly. So, in that case we can find out the values of heat transfer coefficient and mass transfer coefficient from the value of the friction factor using something called analogies. So, these analogies are also taught separately in the courses on transport phenomena. So, in many ways we find the knowledge of the friction factor is often needed to solve the engineering and scientific problems. Okay. So, with this brief introduction on the friction factor, let us go to this problem, in which we have been given a relationship between the friction factor and the Reynolds number. And we have been told the Reynolds number is 10 to the power 5. Now, generally what happens that in a circular pipe there is a critical Reynolds number which signifies the transition of the flow from the laminar to the turbulent. Okay. Generally for a circular pipe, this critical Reynolds number is about 2000 or 2100. So, beyond this there will be some transition zone and very high flow rates when the Reynolds number also goes high. So, we have turbulent flow. So, in this case the Reynolds number value is 10 to the power 5. So, it is quite high, and so this particular flow is turbulent. Now, here you see that we have to find the value of the friction factor for the Reynolds number, and we have to use various kinds of methods we have studied so far, and each of these methods may be used to find out the friction factor for the given Reynolds number. So, let us take each of these methods one by one. So, first we go with the successive substitution method. In this method, as we learnt earlier, that we have to rearrange the equation to get the value of the unknown variable explicitly in terms of the other variables, and this arrangement may be done in a various manners. That is, there is no unique way of representation of the unknown variable from the given equation. So, here what we shall show you, that if we assume one kind of representation, how the solution is going to proceed. So, let us see that this is the one representation I have shown you here. Here what we are doing, that we are basically taking square on both the sides and then we are taking the reciprocal. Now, when you square this whole equation, what you find, that this under root f becomes f, and then you take the reciprocal of this particular equation. Okay. So, that is how we find that we are getting this equation. Now, whenever we are going for this method, what we do, we start with some initial value, and from that we keep updating this value of the unknown variable using the equation we have just written. So, here that is why we are writing here that this we take as the unknown and this we take as the value which is coming from our initial guess or from the previous iteration. So, here we are writing f k plus 1, where k signifies the iteration level, and this everything remains same, and here on the right hand side we are writing f k. So, that becomes an explicit way of finding the unknown variable. So, implement this, what we do, we start with some initial guess, and that we are putting as f0, because we have not started the iteration yet. So, we are putting it as 0, k equal to 0. Okay. So, now we have f0 equal to 0.01. What we have to do simply is that put this value on the right hand side of the equation we just showed, and with this value we get the updated value of the friction factor. So, we find that this is coming out to 0.0041. So, you can see that from the initial guess of 0.01 we have come down. Now, understand this, that depending on the initial guess, this particular value will also keep changing. Now, with this particular value, again we can go for updation, and we see that this particular value we are obtaining, next value we are obtaining by putting the latest value, and again we are getting the updated value. Now, we can keep proceeding with this kind of updation until convergence, and as I mentioned to you in my lecture, that convergence means that the user would specify whether we are approaching the true solution, that is what we call accurate solution, or precise solution, that is whether the two consecutive values of the unknown parameters are getting converged or not. So, in this case we can see that 0.01 and 0.0041, they are different, but again it will depend on the user specified criterion for convergence, whether we should continue or whether we should stop our iteration. So, here you can I have put these dots to tell you that this continuation of this method would depend on the user specified convergence criterion. Now, another way somebody can say that we may get the value of f from the same equation is this. Now, you can see the equation pattern has changed. Now, in this case you may also get the value of f. Now, it will again depend that whenever you are starting with some new value from some initial guess value, whether this new pattern of the equation would give us convergence or not. So, you may check these different types of these representations in terms of the convergence. So, here you can see that we are putting this method for some other methods, like successive substitution was that here we just needed to rearrange the equation to get explicitly the an equation for the unknown variable. Now when we go to the other methods as given in the problems, we find that that kind of rearrangement is not necessary, but now we have to put this particular equality in terms of an equation. So we are given this particular equality. Now what we do, we put in terms of equation, so that what we need to do, that we take everything on one side. So in this case what we have done, we have defined another new function, okay, that is in terms of the friction factor, and we have taken this particular term on the right hand side. You might as well take the right hand side on the left hand side. So it does not change the solution. So let us define this new function capital F as a function of small f friction factor like this, and this we are putting as 0, and we are putting the value of the Reynolds number. So we are having this particular equation, and suppose the convergence criterion is given like this. Okay, this is arbitrary, you may choose some other convergence criterion. Now let us go to bisection search, and as we learnt earlier, this particular method needs the root to be bracketed for the initial guess values, and we know that this particular method needs two guess values initially, and that particular guess values, they will define the domain within which the particular solution would lie, and we can keep chopping off into half this particular interval, so get into the solution. So what we do here, that we choose these two values arbitrarily, and what we see, that we check the values of the function. So we put once this value and then this value and check the values of the function. Now what we find here, that when we take the product of these two values, it is coming to be negative. Even without taking the product, you can also, by observation also, you can check that if the two function values are coming out to be negative, that means that the root must be lying within this zone. So it is just a coincidence that for this particular range we have selected arbitrarily, the actual root is getting bracketed between these two values. Now what we are doing is that we are now to find the new values of the root, we chop off the initial range. So what we do, we bisect, that means we are dividing by 2. So we take the initial two values, bisect it, and we get a new value of f. And now what we do, we find again the function value for this new value of f, and we find this is coming out to be negative. It shows that now our region of search has now shrunk, and when we take this product between f1 and f2, and we find it is coming to 0, and when we take for ff0 and ff2, we find it is coming to negative. It means that now the region has shrunk between f0 and f2, and f0 is 0.002 and f2 is 0.006. Now new search domain is 0.002 and 006. Now with this, what we do, again we bisect it to get another estimate. So here we find by bisection we are getting 0.004, we find the function value at this new unknown variable, and we find this is coming to 1.01. We again take the product between the function values for these pairs. So f0 into f3 is coming positive and f2 in f3 coming negative. It means the new search zone should be between f2 and f3, and now this is f2 and this is f3. And now you can see that you can now carry out this particular iteration and keep on shrinking the domain of your search. Now from this particular thing you see that it seems that the domain of the search is now moving closer and closer, and the next value, next search will be 0.004 plus 0.006 divided by 2, that is 0.005. Now again you have to take the function value at that point, and you can see that how we are slowly and slowly able to shrink the domain of our search for the root. Next we come to another bracketing method, that is the regular falsi method, and in this case, in this we are taking some slope value here, and here also we need the evaluation of function values at 2 points. So here we need also to start with two initial guesses. So what we are doing here, we are taking the initial guesses same as we have done for the bisection search. So here we have to just simply find out the function values, which we are doing it here at point f0 and point f1, and here are the function values, and we can see that f0 and f1 coming less than 0. So we see that this f0 and f1 are able to bracket the roots. Okay. Now after bracketing the root, it becomes now easy to implement this particular method. So we find the function values at these two assumed values, and we are finding these function values, and we have put these values over here, and we generate the value of the next updated value for the friction factor, and this is coming out to this. Now again we evaluate the function value with this new friction factor, and we find that this is the value of the particular function. Now here you can easily see that if you multiply this with this particular ff1, you will get a positive value. If you multiply this ff2 with ff0, you will get a negative value. Now that means that the new search domain should be between this f0, that is 0.002, and the f2, that is 0.0067. Okay. So with this, what we do, we find the next updated value, that is f3, and again we find that f3 is coming 0.0054, and at this f3 we are finding the function value, and this is coming to a positive value. So as we have done earlier, we again take the product, and we can keep on finding the new search domain. Next we come to another method that is similar to the regular fallacy method, but this differs in the way that in this case we are not bothered about bracketing the root. So it is an open way of finding the root. So here what we are doing, that the formula remains the same. Now what we are doing, that we have just changed our initial guess values. So instead of taking it 0.002, we are taking it to be 0.007 and 0.01. And when we find the values of the functions at these two guess values, what we find that they are both positive. But here we do not bother to check for any kind of sign of the products. We simply go with these two values and find out the next value of the function. So here we have that we find that with the function value, this new value is coming out to 0.0025, and as we have discussed earlier, that depending on the nature of the function, you can also see the nature of function, whether it is decreasing or increasing. We can check that f0 is decreasing and f1 is more. That means the seems that if we go from f1 to f0, we will be able to go towards the root. Okay, because root means that this capital F value should be 0. Okay. So since we are going towards 0 in this direction and not the other direction, that means what next we should choose this one and the new value for our search purpose. Okay. That is how we keep on eliminating the these values of the unknown. So what you can do now, you can go with this kind of things, and we find that you keep finding the values of this new value, and again keep checking that in which direction you are going to go, and you keep doing these things, and slowly you also find that you are able to approach the root. Next we come to a very effective method, that is Newton-Raphson. And as I told you, this method works the best among all the methods, provided the initial guess value is nearby the actual root. It will not be working well if we are much too away from the actual root. It may also diverge, or it may show oscillatory nature in convergence. So that will not work out. So here what we do, we put this function value here, and as we learnt earlier, this particular methods needs the evaluation of the derivative of the function. So in this case, we shall take the derivative of f with respect to the friction factor. This f prime f shows this is df by df, that is the derivative. So once we put this particular expression for the derivative, what we now do, that we go to this recurrence formula for the Newton-Raphson method, and again we start with a guess value for k equal to 0, and let us take it arbitrarily to be 0.01. Okay. Now, with this 0.01 we find out the next value, and after iteration 1 this coming down to this particular value. Okay. And then what we do, we take this new value to get the next updated value, and this is coming out to this. Now, you can see that it seems to be fluctuating, that from 0.1 it went to 0.00045 and again it moved up to 0.001, and so you may carry out this particular method and you may find that there could be some kind of oscillations that may lead to divergence, or that may also lead to the solution, but it is not going in a very smooth manner. Okay. But now, if you look at the previous methods, bisection, search, etc., you will find that this kind of nature is coming for Newton-Raphson that may give us some wrong notion as if Newton-Raphson is not an effective method. But then you must remember that this method works well when we have the initial guess value good. So, with this particular guess value, it seems that this is not a very good guess value. Then what we do, we take another guess value 0.007. Now, when we take this particular value, now we can see that if you use this value, how fast we are getting towards some kind of converging value. Now, you see that 0.007, it was brought down to 0.0035, then it is going to 0.0043, and then it is moving to 0.0045. We are almost reaching the convergence with this particular method. So, you can see that this Newton-Raphson method highly depends on the initial guess values. Summarizing all these methods, we can see now that how these methods work. I have shown you the various methods and the iteration level here, and you can see for the bisection search how this region of our search is decreasing. Okay, it is still long way to go, and understand this, that Newton-Raphson seems to be converging towards this 0.0043 value. Now, with respect to this particular value, you can see that all these methods are moving definitely towards a solution with shrinking domain of search, but it seems that their search domain is shrinking a bit too slow and much slower than the rate at which the Newton-Raphson is able to move towards the solution with a good guess value. So, this particular table clearly tells us that the efficacy of the Newton-Raphson method, and if the Newton-Raphson method is to be implemented, we may not be able to do it right away. What we can do then is this: we can check any of these methods which all of them seem to be going towards a more and more shrinking zone of search, so that with one of these methods we can first generate the right domain of search of the root, and then we may move on to Newton-Raphson once we have located the search zone, or we have found the direction in which the solution should be taken. So, we may say that we may use some kind of hybrid way of finding the root of the solution for any kind of nonlinear algebraic equations. More of these may be studied from these particular references. Thank you.